Alright, we looked at fx equals 2x, and what we did was we calculated the gradient dy by dx by way of utilizing the formula fx plus h minus fx divided by h, and what we found was the gradient was 2, which we were comfortable with regards to that. We also then looked at y equals x squared, and we used the same system, went through all the steps to find that the gradient was 2x. And what we did was we went through the reason as to there being an x in terms of the gradient, suggesting that what that x does is it allows for us to pick where we want to calculate the gradient, because for a quadratic, the gradient changes. That is where we were. Now what we're going to do is we're going to apply this to, first of all, finding a straight line that fits a certain point, and then we're going to look at a cubic. So first of all, if we're going to find a straight line that fits a certain point and matches the gradient on our quadratic, one of the things we need to be aware of course, is the equation for a straight line. Also, in terms of language, this straight line that matches the gradient of the curve at a certain point is known as a tangent line. So we're going to find the tangent. So first of all, I'm going to take this equation of y equals mx plus c. We're going to do it at x equals 1 purely because it's an easy place to do it. So when x equals 1, we know y equals 1 simply because if 1 squared is 1. And we know that the gradient will be 2 times 1. Remember that the gradient was 2x. So therefore, if I'm going to make it at x equals 1, it'll be 2 times 1, and so the gradient is 2. So I have these three pieces of information: x equals 1, y equals 1, m equals 2. My question then becomes, what is the equation of the line at that point? And the way that we work that out, I simply make sure I'm aware. I plug in my x equals 1 into y equals mx plus c. The x therefore becomes 1. The gradient was 2. I can plug that in there. There's the gradient being 2. And the value of y equals 1 I make for there. And then once I've plugged all that information in, I get to be able to rearrange. It'll be 1 equals 2 plus c. So if I move this 2 to the left-hand side, this 2 is going to go to this side over here. It'll be 1 minus 2 equals c. And 1 minus 2 is minus 1, so therefore c equals minus 1. Therefore, if I have y equals 2x minus 1, if I have y equals mx plus c, this equation here, I know the gradient is 2, so I plug that in, and I know that c is minus 1, so I plug that in. I get this straight line here going through the intercept c of minus 1. The gradient was 2, and notice that at x equals 1, it is a perfect match. So that is the tangent of the curve at x equals 1, which I was able to calculate as a result of knowing that the gradient was dy by dx equals 2x. There. Now what I want to do in addition now is look at the function fx equals x cubed. I'm just going to put it in the form y equals x cubed for now, because I judge at this point many individuals might be more comfortable with this, perhaps. And so what I'm going to do is I'm going to utilize again the formula. Once we figure out the pattern, we won't have to continue using the formula, but at this stage in the course, I want to keep using that formula. That formula being, of course, as stated at the top here, dy by dx, or delta y divided by delta x. The gradient is equal to fx plus h minus fx divided by h. So what I'm going to do, first of all, for the cubic, fx plus h is x plus h cubed. And you can see that while I can expand this out using such things as Pascal's triangle, but I'm going to do it the dodgy way just to get this repetition in. I'm splitting this up into 3 as it is suggested because it is a cubic. I then can multiply out in this manner. So x times x is x squared, x times h is hx, and hx and hh, leaving me with x squared plus hx plus hx is plus h squared. And then I have this left over here. This comes from this part. Then in addition, what I can do is I can then finally bring these two together. So these are the same species, of course, hx times hx giving me 2hx. And then finally, I can then multiply this out accordingly. So x squared times x squared, let's make that a little bit more accurate, x squared times x squared times h, 2hx times 8x, 2hx times h, and so on and so forth, leaving me with this lovely elaborate equation here. What's nice about this, however, is things come together quite nicely in this. For example, there's 2hx squared, right? And then there's also an hx squared here. 2hx squared plus an hx squared is 3hx squared. You can see that these two also join up. The rest come in nicely like so, and I've got this equation. I'm going to be able to utilize this for fx plus h. So I'm going to do that. Fx plus h is fx plus h here is instead replaced with this. I have f minus fx. We know fx in the first place was the actual cubic, so fx I'm going to change into that cubic. If I zoom out, you can see me do this. This fx part of the formula, I simply make sure that it states that it's the cubic, x cubed. And so there you see everything nice and neat. You may also notice certain things start to cancel. For example, cancel, cancel, and then I'm left with this here. But this also has quite a lot of lovely cancellations in it. For example, h will cancel with that h, the h squared will cancel with it, and the h cubed will become h squared and cancel with it as well. Hence, I'm left with this equation here of x squared, 3x squared plus 3hx plus h squared, lovely there, and then 3x squared plus 3. Now, what I'm just trying to describe here is this phrase. Let's take a more of a look at this one. The limit as h goes to 0. Again, I think I might have described this in the last video, but the point really is that if you're going to find the gradient at a point, you want it to be as tight to the point as possible. So you want your triangle to have, let's say for example, you want your triangle to have a very small base. You do not want it to be too large, because that will allow, the larger I make this triangle, the more I will get inaccuracy. So for example, you can see here that if I were to, I don't judge, I have the mouse skill for this, for example, but if I make this larger, you can see that there's some difficulty in saying that it's accurate or is as accurate as it can be, because the larger I make it, the more likely that there is some error accruing due to the size of the triangle. When the triangle is tight and small to the point that you want, right at the point, the gradient will match well. And what can be said about this? Well, one thing that can be said is the h, or which is this length along the bottom here, is small. And we say that h goes to 0. So that's what we're going to do here. I'm going to say the limit as h approaches 0. It is not 0 per se, because if it were, the triangle would collapse. We say it's the limit when it approaches 0, and hence this, I do have the capacity to say such things as this h therefore becomes 0 in here, and this h squared becomes 0 as well, leaving only 3x squared. So the equation therefore for the gradient is 3x squared. And notice I don't have to utilize these delta signs anymore. Once I'm taking into account the limit as h goes towards 0, I can use dy by dx. So small that it's not something that is measurable by way of such things as ruler, for example. So we've got dy by dx is equal to 3x squared, and that is our cubic. That is the gradient for the cubic, and I can pick any point I want along that cubic by putting in different values of x there. Now let's do a slightly easier one. So I'm going to get easier just because at this point all I'm looking really to do is show you a pattern which will allow us to no longer have to utilize that formula again and again, which, as you can see, is becoming relatively tedious. So that is to say, let's take fx equals kx. Now one thing to recognize, one thing to recognize is that k could be seen as kx to the power 0, because anything to the power 0 is 1. This is the equivalent of, this is still equal to k. This is the same as equals k, but I'm putting x to the power 0 because I want to use the formula just to be a little bit eccentric here, but also to drive home the point of what happens when you have a constant. So here, fx is just going to be kx to the 0, fx plus h, therefore, similar to the pattern we followed before, x is now being replaced with x plus h. This becomes kx plus h to the power 0. I can plug all this information into my formula. Instead of fx plus h, I'm only going to plug in, by the way, x plus h to the power 0 is 1. All of this becomes 1, so that's why it's just k, of course. Now, I can therefore just say, instead of x plus h, I'm just going to put in k. So that's that change there. Fx we know is k, because it is the original equation I'm trying to do, y equals k, fx equals k. So therefore fx is k, as I've stated up here. So I'm going to plug that in, fx being k, like so. And then what do we have? We have k minus k, which is 0. 0 divided by h is 0. So when you have a constant like the y equals k, which would be a straight line at a certain, so for example, if this was my y-axis, and if you were to believe that this is my x-axis, y equals k would be a straight line, say for example, let's say k equals 4 and it was 1, 2, 3, 4 up, it would be a straight line across here. You can see that there is no change in y relative to change in x, because change in y is 0, as is depicted here. The change in y part is 0 because we'll change the base change in x is h. Of course, that still relatively exists. There is still some base, of course. You can perhaps argue that if you wish, but there is definitely no change in y. That's why it manifests as 0, and so there is no gradient. The gradient is 0. Let's look at some more patterns here. When y equals 1, 2, 3, 4, 5, or 6, or whatever, as we have already shown for k, that is any constant, we know that dy by dx is 0. So that's something to recall. When y equals x, 2x, 3x, 4x, 5x, 6x, kx, a billion x, whatever. If you go through this pattern, you will find, I think we tackled this one quite early on, you will find that we tackled, I think we tackled y equals 2x, and in the end we got a gradient of 2. Whatever this is, whatever this constant is in front, so it was 2 here, 3, 4, whatever it is there, you will find that it is the exact equivalent. Whatever that coefficient is the equivalent of the gradient. So for example, I said here when y equals 1x, 2x, 3x, 4x, 5x, and kx, you will find that the gradient is 1, 2, 3, 4, 5, k, whatever, so on and so forth. So we've got a pattern. If it's a constant, it's 0. If it's a coefficient of x, it is the coefficient. What happens when we have a quadratic? Well, when we did x squared, we got 2x. If you had 2x squared, and you can do this if you wish, I would suggest you have a go with this. That's why I've stated the phrase try these yourself. If you have 2x squared and you use the formula, you will get 2 times 2x as your gradient. If you have 3x squared and you use the formula, you will get 3 times 2x. If you have kx squared, you will get k times 2x, respectively. So this is, again, a pattern that's emerging. I'm going to summarize all of this together at a later point. Now, y equals x cubed. What did we find from that? Well, we got 3x squared. And again, note, and again, have a go, try these yourself. Note that if you had x cubed, 2x cubed, 3x cubed, kx cubed, guess what you would get? Well, you will find that you would have 3x squared. That's what we got from the one when we practiced. If it was 2x cubed, you'd have 2 times 3x squared. If it was 3x cubed, you'd have 3 times 3x squared. If it was kx cubed, you'd have k times 3x squared. And again, if I'm going too quickly with regards to that, please have a go yourself. The one that we've definitely proven ourselves is that when y equals x cubed, you get a 3x squared as your gradient. And I'm suggesting that maybe if you have a go practicing these versions, you'll end up with an idea that means that the power reduces by -1 and it becomes the coefficient. So anyway, regardless, if that was too much cognitive load, let's just simplify things in this manner here. When y equals k, dy by dx is 0. When y equals kx, dy by dx is k. When y equals kx squared, dy by dx is k2x. When y equals kx cubed, dy by dx is k3x squared. When y equals kx4, dy by dx was k4x cubed. When y equals kx5, you perhaps are starting to get the point. It seems to be that when y equals kx to the power n, the gradient is knxn minus 1. And this means that for a polynomial of similar to those that we've been tackling, you could utilize this rather than doing the equation again in the manner that we've been doing it. And this might be a lot faster. I'm even just being a bit too polite. This is extraordinarily faster than having to go through such things as working it out with that formula. And so, thus, let us see the degree to which we can utilize this to get the same situation with more challenging problems. So here's one little weirdo function here. We've got y equals 4x to the 7 minus 3x cubed plus 4. You can see it's a lovely, interesting one there. And what is the gradient? So if we were to utilize the formula fx plus h minus fx over h, you can see that that might manifest in some weirdness. I'd have to put x plus h in here, and I'd have to put x plus h in there, and I would then have to expand them out to the cubic. We've already done, but to the power 7 is extraordinary, and I definitely want to use Pascal's triangle for that. It's a little bit odd for me to do all of that work just to find the gradient. Not my style at all. So what I'm going to do instead is I'm going to use our formula that we found from just the pattern that arises when we use the formula fx plus h minus fx over h. If you do that for all of these types of functions, this one, this one, this one, this one, this one, and this one, you will find that you get these outcomes, And this pattern has led us to this lovely equation here, which we're about to use. So let's see if we can do that to find the gradient for 4x to the power 7 minus 3x cubed plus 4. Well, first of all, what is the pattern? The pattern is you take away 1 from the power. Let's do this by way of my, on this one here, and then by then I can show you it on the next page. So what I'm going to do is I'm going to take 1 from this power. It'll be 7 take away 1. 7 take away 1 will be 6, so that should be 6. That will happen after I bring down the 7. So there'll be a 7 in front, then it'll be 7 times 4, x to the power 6. The 3, I'm going to put that in front, so it'll be 3 times 3, x to the power 3 take away 1. And this 4 here, what is the 4? Well, let's not forget the 4, it could be said to have this x to the power 0 here. So it'll be 0 times 4, which is 0 anyway, but then it will be 0 to the power 0 take away 1, which regardless doesn't matter because it'll be 0 times this, so this will all become 0. Watch this space. So here you can see I do it. The 7 came in front, 7 take away 1 was 6. The 3 came in front, 3 take away 1 was 2, and the 0 manifested here, leaving me with 4 times 7 being 28 to the power x to the power 6 minus 9x squared. That is the equation for the gradient, and we did that so much faster than if we had used the formula. Some might be shocked, but don't be. It's relatively peaceful process, and it makes quite a lot of sense. If you are shocked, that's great. That means the math is really hitting you. Anyway, let's take a look at finding a tangent like we did before. We'll finish off with this, and then we'll leave it there. So let's say we want to find a tangent. What did we learn about the tangent? It is a straight line at with the same gradient at a certain point. Let's do x equals 1 as our position, just be out of tradition. We've done that before. Well, first of all, I want to know what y is. So to do that, I take my original equation of this. Let's neaten this up, make it look a little bit less nasty. So clean that up like so. If I've got my equation y equals 4x to the power 7 minus 3x plus 1, and I need to know what the y value is at x equals 1, I'm just going to put a 1 in here. So it'll be 4 minus 3 plus 4. So I'll have that as my capacity to calculate my y value. So you can see here y equals 4, 1, 7 minus 3, 1 cubed plus 4. That's just 5. Of course, 4 minus 3 plus 4. So in this situation here, I know that when x equals 1, y equals 5. Let's double check that. I've given us a graph. Let's scroll up from x equals 1. Let's see if we can do this. So from x equals 1, what do I get? If I go from x equals 1, I go all the way up until I touch the graph. Oh, look at that, not bad at all. We get y equals 5. So that's something that we can feel quite comfortable with. Now, what was the gradient? We calculated dy by dx was 28x6 minus 9x squared. So what is it when x equals 1? Well, to do that, I'm going to, of course, put a 1 for my x there. I'm going to put a 1 for my x in here. I get 28, 1 to the power 6 minus 9, 1 squared, which is 19. So now I know that my gradient is 19, also known as m. So I know that to be the case. This is my m here. I also know that my x equals 1 and my y equals 5. I can use this to calculate my c. So I state comfortably, I say, well, if it is a tangent line equals y equals mx plus c, there's me saying it. What do I know about the gradient? We know the gradient is 19. We know that x is 1, because that's the one I chose. I know that y turned out to be 5. 19 times 1 is 19. If I want to move that 19 to the left-hand side, I'm simply just going to move it there. It becomes minus 19. 5 take away 19 is minus 14. And so c is minus 14. I state my new equation like follows. The gradient is 19. The constant is minus 14. And what happens when I plot this? Is it the correct tangent at that point? Did this system work relative to utilizing fx plus h minus fx over h? The answer is yes. Yes, it did. Where at x equals 1, you can see this is my tangent line. It is touching it exactly where it should, for want of a better phrase. And you can see when x equals 1, y equals 5, the gradient is exactly how it matching at that point. And so that blue line is my tangent line of y equals 19x minus 14. And with the weirdest, not too weird, but with a relatively elaborate function, I've been able to calculate the gradient and the tangent line without having to utilize this formula, but at least I'm aware where this pattern came from, which we are now going to use going forward, and the fact that it is the manifestation of us utilizing our fx plus h minus fx formula on multiple polynomials to the degree we found a pattern, and now we can utilize our equation born from that pattern to differentiate multiple polynomials going forward. And that's what we will do in the next video. Thank you.